lots of things. Okay, so the idea is here, I want to give an example of what's going on. So that this has nothing to do with linear algebra, but it should be something you understand in terms of numbers. So it shouldn't, so we can just isolate the new part about proofs without having to involve lots of other stuff. So it involves the concept of a factor. Like, for example, 3 is a factor of 6, because I can write 6 equals 2 times 3. So we say 2 and 3 are factors of 6, right? And so that is probably, so there's a notation for this. We can write 3 is a factor of 6. And what we mean by that is, this is also divides. So we can write this as 3 is a factor of 6, or 3 divides 6. What we mean is, if I divided 6 by 3, I get an integer as a result. I don't get any fractions. So when I make this thing, so what I can say, is that if I choose numbers A and B, this is the claim. It's either true or false that A divides B. So, for example, 3 divides 6 is true, and 4 divides 6 is false. Okay, so here's a claim. We want to see if we can show, I want to prove this is true. Okay. We let A, B, and C be integers. Okay. Then, if A divides B and B divides C, then A divides C. Now, one thing to do when you confront with something abstract like this is to just sort of do an example. For example, we have, let's say, okay, what if 3 divides 6 and say 6 divides 36? Because I know that 3 times 2 is 6 and 6 times 6 is 36. This would be the claim then that 3 divides 36. And you can see that that's going to be true from this, but it might be that these would be understandable and this wouldn't be so clearly true. So that's the value of something like this. Now, the question is, this is an example, and you can sort of intuitively sort of see that, well, if A divides B, it's got to be a factor of B, and if B is a factor of C, well, inside it's going to have 3 as a factor. So you can sort of see that it's going to be true, but how did you show it's true? Well, there's a way to analyze, and we're going to analyze how to do this, how to sort of analyze how to prove this, because what a proof is a very careful, precise argument that doesn't let any loopholes get in the way. And so it's a game you play, that mathematicians play, that's a little different than you're used to. And one reason for introducing it is, well, 2 reasons are. The first reason is that a number of linear algebra concepts are proof-like. So it's very helpful to understand linear algebra to understand how proofs work. The second way is, when you write a program, the kind of thinking you do is a lot like the kind of thing that goes into a proof. So if you don't need to do proofs to be a good programmer, but if you do sort of practice a proof, it will help to put you in the frame of mind that you need to write, to be very demanding of your logic and thinking when you're writing a program. And there's a third reason, that many linear algebra courses are quite different. There's like engineering courses, there's more like math courses, and then there's application linear algebra courses. And this is more like the math one, okay? The one reason for that is that when you try to transfer this course to a 4-year school, that they're going to want to know that it has calculus as a prerequisite, and they're going to want to know like some schools have different courses for all those 3 arenas. And they're going to want to know, did you have an engineering course in which they might not give you credit for it, or did you have a math course? So a math like linear algebra course. So like right now, there's someone who's applying somewhere, and the school wants to see the textbook and the assignments, and they want to see everything about it to determine whether they're going to give one of their math-based students who's trying to transfer school credit for this course. So that's one reason for including this stuff in the textbook and then including it in the course. So you see some of this. So it increases your chances of getting at all the Massachusetts schools. There's no issue. It's just when you go like to some out-of-state school, or you go to some sort of like I think Cornell. One person had a lot of difficulty getting credit for it because Cornell, well, they just didn't want to give credit to any. There's sometimes they think they're sort of better than anyone else, and so they don't want to give credit to other schools for their stuff. Okay, so those are the reasons why we're doing this. So there's a strategy for discovering a proof, and the strategy is this: you write down what you suppose or assume is true in one column, and you write down what you have to show in the other column. So what do you assume? Well, A, B, and C are integers. So we can just use facts of numbers, like all the facts of high school numbers as that. And then, well, that's basically it, right? And then we want to show that A divides B and B divides C implies A divides C. So it uses this if-then statement. Now, what you have to do is to try to transform these two columns by looking at the pattern, the thing we have to prove, and there's a number of proof patterns. So the first proof pattern is, if you have to prove P implies Q, what do? Well, you assume P and show Q. Why is that? Well, this is going to be, the only way this can fail to be true is if P is true and Q is false. So if you assume that P is true and then show that Q is also true, you've shown that can never happen, because you'll never have the case of true false. So this is the slogan. If you have and we do have a conditional here, whereas this is the P and this is the Q. So we can transform our assume and show table into A, B, and C. I'm going to write this with symbols, are members of Z. Z is it's the German word for Zahlen, like. So that's why Z was chosen for the that. Now, since I'm assuming P, I'm not saying this is true. I'm assuming it's true for the sake of this proof, and I have to show. So now, instead of having to show this big thing here, I get to assume a bunch of stuff and more stuff. So I've moved something from the show column to the assume column using this proof pattern. Okay, and then there's a second one is, this one says there's some common rules of deduction. This is, so if I have two things that are true, I can choose either one of these to be true. This one implies that both A and B is true and B and C. So this is sort of like when you have a conjunction, you choose each truth. We'll see some more of these patterns. So that allows us to again make this change to simplify what we're assuming and showing. Okay, A, B, and C are integers. And we have A divides B and B divides C, and all we have to show is A divides C. Now, this is sort of a concept. What we need to do is, when you have a concept, you want to replace concept with definition. So, what is the definition here? Well, A divides B when there is an integer, say r, such that b equals r times a. So it's like what it has to be is there has to, if a is a factor of b, there has to be a number r, so a times r is b. That's what we mean by there's a factor. Okay, you don't have to be given this. I mean, you'd have to know this from that. This was how this concept was defined. But now, if we want to replace this definition, what we can write here is we can write assume and show, and then well, a, b, and c are integers, and then we have a divides b. Well, this means there's an r. There's an r such that b equals r times a. And then there's a q such that c equals q times b, because this first one was a divides b, and the second one was b divides c. So there has to be a number of q such that b times q is c. And the show one was a divides c. So that's going to be, there's a rq, say there's a t such that c equals t times a. Okay. Now, this is actually much more concrete. So what I need to have heart now is what I need to show is I need to show that there's a number t given that c equals q times b and b equals r times a. But this requires some insight, realization. Well, look, if I substitute b in there, so this is the sort of, you've reduced it to something which is concrete, but it requires a little insight. So if I put those two together, I can see that c equals q times r times a. So that equals q times r times a. So then if I choose t, that shows me, given these things, I've found the t, right? But that means I've shown that a divides t. So that means that I'm sort of finished with the proof. Now, I have written out all of this stuff here in this following thing here with the assume and the show and the proof pattern going here and how to use a conjunction. And then when encountering a definition, this is all written out. And then here's the heart of the proof we just get to. And so then here's an outline of what these patterns we've done. And then what you do once you found this sort of the heart of the matter here is this sort of outlines all this logical stuff. But when you write up a proof in Mathlish, so to speak, it omits all this. So it's just the tip of an iceberg that gets to the heart of the matter. The heart of the matter is this thing here. So the way you write it up is say, let A, B, and C be integers. Suppose that A divides B and B divides C. That's suppose. That's the first bit when we not that far back, when we went and changed it to, let's see where. Yeah, when we went from this point, we have the implication on the right to this on the left. That's where this is the case we're using the proof pattern of the conditional. Then there are integers q and r such that b equals q times a and c equals r times b. Well, that's the definitions of what we mean by a divides b and b divides c. Then we can see that c equals r times b, which equals rqa, because I'm substituting that in there, which means that C equals R times Q times A, which is what we mean by A divides C. So you're done. And then every proof you formally begin with the word proof, and you end with like a special symbol. The purpose of these two symbols here is what occurs here is like in strict Mathlish. It's sentences, but it's not really English. It looks like English, but it's really strict. Now, outside this thing, you could have more examples, more colloquial, descriptive stuff. So if you look at this, it would be hard to sort of understand what was really going on when you only have this short cryptic thing, when in fact, there's actually quite a bit of machinery underneath. But then for almost all the proofs that we look at, there's going to be something like this where you can understand in detail how to first take the seemingly impossible statement and make it concrete, where you can have the insight of how it works, okay? And oftentimes when I do have a proof or something like that on an assignment, what it means is you need to sort of write out your first attempt and come and talk to me, and I'll critique it, because it's sort of like an essay in which you have a rough draft, and then you need to check it with the instructor who will critique it and give you suggestions, and then you rewrite it as a final draft. So rather than being just a test that you go and do it and turn it in, but that means you have to do it earlier rather than at the last minute. If you're doing it like on the Sunday before it's due, then you don't have time to go through that revision process. Okay, so let's